Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a simple analysis of three levers: first class, second class, and a third class lever that you can find around your house. So I don't have a rowboat. That would be cool if we analyzed these oars. We actually did analyze a hammer in class, but we were swinging the hammer, not prying a nail out of the board. Somebody in class said they had a wheelbarrow at home. That would be awesome to analyze that. And I think we talked about the fishing rod also. Okay, so pardon the scrolling. Let me try to page down. No, hang on. Page down here. Okay, so the garden loppers, these guys right here, were on my first simple machine. It's actually a complicated, I don't know, gear 4-bar mechanism thing going on up here. So I just pretended that there was a simple pin joint. Hang on. A simple pin joint up here. You can call it the fulcrum. You can call it the axis of rotation. And said, all we're doing is measuring how far the two forces are in relation to the fulcrum. So if this is the pivot, this pin joint up here, the resistance is the blade, the business end of this tool. So how far is it? I measured it to be 1.5 inches or 3.8 centimeters in between the pin and this blade. That is that distance right there. The handle, as you can see, is really, really far from the pin joint, so that's called the effort distance. I measure that to be 26.5 inches or about 67 centimeters. And once you have those two distance measurements, it's just a simple ratio. Ideal mechanical advantage is the effort distance divided by the resistance distance. Excuse me, and in this case, that's 26.5 divided by 1.5, or around 18. So what is mechanical advantage? Well, you can also call it the force multiplier. If I put in 1 pound of force down here, I'm going to get 18 pounds of force right here. Why? Well, my input torque is the output torque, and this is really the mathematical relationship that describes what's going on. So a small force applied really far from the pivot has the same torque as a very large force applied a very small distance from the pivot. So, that's why the ideal mechanical advantage is the ratio of distance, effort divided by resistance. All right, let's analyze my second lever, the lemon juicer. All right, so here's the actual tool. Here's my concept sketch. The load this time is in the middle, kind of like a wheelbarrow. The fulcrum is this pin joint right there. And I measured that distance, that is how far the fulcrum is from the lemon, to be 2 inches or 5.1 centimeters. And where your hand goes down here, that's the input force. So I measured that distance, the effort distance, to be 7 inches or 17.8 centimeters. Okay, so here we go again. Ideal mechanical advantage is effort distance divided by resistance distance. It's really the input torque I'm applying being equal to the output torque. The product of the radius and the force are the same. Because the system's in equilibrium, so the sum of the torques has to be 0 because there's no acceleration, like as you're crushing that lemon. 7 divided by 2 is 3.5. Obviously, inches divided by inches is 1. So there is no unit label for a mechanical advantage. It's a pure ratio or a dimensionless quantity. Soon we're going to analyze wheels and axles. And so this is the side view. Here's the big radius of the wheel. Here's the little radius of the axle. And so if you input the force on the big circle and output the force on the little circle, you get a force multiplier, kind of like you're lifting the bucket out of the well right here. So, this doesn't look like a wheel and axle, but soon I will convince you, soon I will convince you to just multiply this lever around until it becomes a continuous wheel, a continuous circle. Anyway, that's a second class lever when the load is inside, that is, in between the fulcrum and the effort, the handle in this case, the second class lever. Let's do one more. The mallet. Okay, so this is part of a musical instrument here. Like I said, we analyzed the hammer in class, and this is a similar setup. So right there is the axis of rotation. The z-axis is coming at you. We're oversimplifying the situation again. I'm pretending the thumb and the first finger are where the force is applied to this machine, and the mallet itself, this is the business end of the machine. So it's less clear. There's no pin joint. This is a saddle joint, and it's sort of less clear where the force is applied. But that distance right there is the effort distance. So I measured that to be 4.5 inches. And then the distance between, my wrist and the mallet, the head of the mallet, I measured to be 9.25 inches. So again, we just do the effort distance, 4.5 divided by 9.25, except this time we get around a half. I did it in centimeters. So you can take inches, multiply by 2.54. That's my conversion factor right there. And, the ratio of centimeters is obviously the same as the ratio of inches. So you're going to get around a half, an ideal mechanical advantage of a half. So that's obviously less than 1. So third class levers aren't force multipliers, they're distance multipliers. The force isn't that great. I mean, this is a very loud musical instrument. So what we're trying to do is move our wrist a little amount and get a big motion in the rubber mallet. So there you go, 3 simple levers. The garden loppers, gigantic mechanical advantage, 18. The lemon squeezer, 3.5, I think. And then the rubber mallet, 1/2. Okay, so you only get out half the force you put in with this guy, but you get double the distance. That's because energy is conserved. A force applied through a distance is energy, and we're going to talk all about that later. Thanks for watching. See you in the next video.